atom at that moment can't scatter a second photon at a time. So if I were to send in a second photon simultaneously, from the standpoint of that second photon, it effectively looks like this one atom is removed. So I've punched a one atom hole in my mirror. Okay, so it's a nonlinearity, but it's not a huge effect because the incoming beam couples to a potentially large number of atoms on the order of the beam waist squared to the lattice squared. So just kind of punching out a one atom hole doesn't necessarily have a big effect on a second photon. So if I wanted to have a big effect, I should really kind of punch out all the atoms of the array. So I need kind of on the order of W squared over D squared photons to kind of blow out all the atoms and make the mirror highly transmitting. So you can have two possible perspectives of this. Realistically, this kind of number, so here's a kind of 10 by 10 array, so maybe there's kind of 100 photons involved. So to have a 100 photon level nonlinearity, so you send in 100 photons and the system starts to do something different. From the standpoint of classical nonlinear optics, so trying to do nonlinear optics with bulk nonlinear crystals, achieving a nonlinearity on the level of 100 photons is actually very, very tough. I don't know that it's been demonstrated yet. So it looks kind of good for classical nonlinearities. But then, for kind of the quantum regime, if I want to have single photons strongly interact with each other, this kind of level of 100 photons to see an effect isn't really sufficient. So what I really want to do is I want to be able to send in one photon and make it punch a huge hole in my atomic array. So there's one elegant way to do that, which is to involve the magic of atomic Rydberg levels and the strong atom-atom interactions between Rydberg states. So Anton has introduced all the physics of Rydberg interactions already. So let me just kind of here summarize the main idea and what I want to use specifically. So I want to use this kind of dispersive interaction between two Rydberg levels. So basically, if I have two atoms separated by a distance d, I bring one atom up to a Rydberg level. I know that the second, the energy of the second Rydberg level will get shifted by amount, proportional to the C6 coefficient, divided by the interatomic distance to the sixth power. Okay? So here's the kind of Hamiltonian for that, which just simply describes this kind of dispersive shift. So far, this is just kind of atomic Rydberg interactions. There's no optics involved yet. To make this useful for nonlinear optics, there's various possible protocols that you can use. I'll just kind of, for somewhat arbitrary reasons, choose something called Rydberg dressing. So basically, the idea is that originally I have my kind of normal two-level atom, which responds to light, and which eventually will form my mirror effect. But then I consider this kind of third Rydberg level as well. And so I put in a large classical driving field, omega, to possibly induce transitions between E and R. But I'm going to consider the regime where my laser field is large, but it's really also highly detuned from the E to R transition. What that means is that in practice, so this is a little bit oversimplified picture, but I think it has the main intuition. So because of the large detuning, it's really unlikely or just negligible that I'll have any kind of population in state R. So I don't really need to consider it as a real degree of freedom. But nonetheless, if an atom manages to make it up to state E, let's say by absorbing a photon, it still kind of experiences quantum fluctuations up to R. And that kind of little amount of time it spends in R allows the state E to inherit a reduced Rydberg interaction, but hopefully which is still strong. So that's the kind of intuitive idea, and kind of math looks like this. So originally I have my Rydberg interaction, dispersive Rydberg interaction between R states. And then through this Rydberg dressing scheme, what I effectively get is that I can integrate out these levels R because they're so far detuned that there's really not kind of real population in there. And then I get a Hamiltonian involving now interactions between the kind of normal atomic excited states with a kind of similar form, but which is kind of renormalized due to the dressing. So it's small, but it's small compared to the bare Rydberg interaction, but hopefully still big for the purposes that I want. And just to kind of make things a little bit more intuitively clear, So to kind of make, I guess more intuitive toy models, I'm going to simplify this, this potential a little bit. In particular, I'm going to assume that this potential, as you kind of shrink the distance between atoms, it goes from kind of being off to on fast enough that I can approximate as a step function. And that when it does turn on, the magnitude is big enough that for practical purposes, I can send it to infinity. Okay? So this distance under which the Rydberg interaction, this dressed Rydberg interaction turns on, is going to be called the Rydberg blockade radius. So what this kind of effectively means in practice is that if I have one atom up in the excited state, and there's a second atom nearby, so nearby means less than the Rydberg blockade radius, I fundamentally can't excite that atom up to the excited state as well because it would cost infinite energy. Now let's consider this kind of 2D atomic mirror, but with this kind of Rydberg interaction added. So I'm going to now consider the reflection of a weak Gaussian beam, kind of like what I did earlier, but I'm not going to allow it to be arbitrarily weak. So it's going to be strong enough that I can maybe have the possibility of two atomic excitations. And just in terms of kind of numerics, now my kind of spin model, the Hilbert space of that will grow like n squared. That's the number of pairs of atoms, distinct atomic pairs that can be excited. So the Hilbert space, is starting to grow, but it's still kind of at least mathematically efficient. I can still put it into a computer. So let me consider the kind of following thought experiment. So I do the same thing. I send in a weak resonant Gaussian beam that focused onto the array. I know that because my excitation, because I know my beam is very weak. In principle, I should have very high reflection of this beam back into the same Gaussian mode, spatial mode that I sent in. And imagine that I get a click. Okay, so I see that one photon was reflected. And I like to ask, what's the likelihood of seeing a second simultaneously reflected photon? So first of all, if I don't have blockade, I kind of argued that seeing a click kind of punched a one atom hole in the mirror. So the likelihood that I can see a second simultaneously reflected photon, mathematically I can capture it in this so-called second order correlation function of light. So mathematically, it's the expectation value of E dagger squared E squared over the expectation value of E dagger E, or the intensity squared, where E here is really the field quantum operator associated with this kind of reflected Gaussian mode. So basically what you find is that without this kind of Rydberg blockade, G2 is basically 1. So 1 is kind of the statistics you would have for, is Poissonian statistics. It's the statistics that a laser would have. And basically says that the timing of arrival of photons is completely uncorrelated. Okay? So you see that G2 is kind of 1 minus d squared over w squared, or 1 over 1 minus the number of atoms that the beam illuminates. So that just kind of indeed shows or quantifies that without Rydberg blockade, the system isn't very nonlinear at the level of single photons. But now imagine I turn on this kind of blockade effect. Again, I know that one atom had to be responsible for creating this click. But now because of blockade, once that one atom is excited, it's impossible that any other atoms within the blockade radius are excited at the same time. So seeing this click now punches out a huge hole in my array with a radius the size of the Rydberg blockade. So if this kind of Rydberg blockade radius is bigger than my beam waist, the beam waist really doesn't see the remaining atoms anymore, and it's going to be transmitted with very high probability. And likewise, the probability of seeing a second reflected photon will become smaller and smaller. So you can kind of see that here. Here's just kind of a numerical calculation where I plot this G2 in reflection as a function of the ratio of the blockade radius divided by the beam waist. And you do see that kind of goes from 1 in the case that you have no Rydberg blockade down to 0 as the blockade radius gets bigger and bigger. And then when G2 approaches 0, it basically means you have essentially it's just impossible to see two photons being reflected at the same time. That's kind of reminiscent, at least at a heuristic level, of what a single two-level atom responds, right? You only receive single photons at a time. So kind of, maybe not so precisely, you can kind of consider this regime here to be a highly non-classical single photon source. So again, it's kind of like a two-level atom. It's kind of like an ideal nonlinear element. But it's kind of cool because at the same time, it involves many atoms. So whereas a single atom has this issue that's hard to couple to light efficiently, here we gain the efficiency of having an atomic ray and interference and collective enhancement. So we get really the best of both worlds. A single atom-like nonlinearity, but the efficient interaction of an atomic ensemble and moreover of an atomic array. So this kind of looking at G2 is highly suggestive that you have a quantum nonlinearity or strong interactions between individual photons. But aside from kind of phenomenology, we can maybe now try to turn it into something useful. For example, like a single photon switch. So the conceptual idea of a switch is, imagine I have two distinct photon modes, A and B. So these could be just photons that are well separated in time, and therefore I can distinguish the two. And the idea of a single photon switch is the following. I have my atomic array, and let's imagine that photon mode A is effectively a qubit, so it can have either 0 photons or 1 photon. If there's 0 photons in mode A, let's imagine that nothing happens to my array. So if a photon B comes in later, it's going to be 100% reflected. And kind of conversely, if I did have 1 photon in mode A, I'd like to completely switch the response of my array to effectively make it disappear, and then this 1 photon B would be perfectly transmitting. So that would be my ideal operation of an array. So this is kind of like a single photon switch, but you can also see that this type of switch creates entanglement. So for example, if I were to prepare my photon A in a superposition of 0 photons plus 1, then the path of the second photon B gets entangled with the state of photon A, okay, reflecting and transmitting. And once you can kind of create this entanglement, it's pretty straightforward to turn this type of photon switch into a genuine photon gate. So I should mention that the idea of using Rydberg atoms to generate optical nonlinearities is not new. This type of, it's kind of similar nonlinearities can also be generated just in kind of disordered atomic ensembles. And it's actually a very active field. So kind of, strong photon-photon interactions are now routinely observed in laboratories worldwide. And there's actually been kind of theoretically proposed that you can create photon-photon gates with Rydberg ensembles. So in particular, these types of gates are always analyzed with the Maxwell-Bloch equations, which ignore interference and which assume independent emission of atoms. And the best known gate error that I know of goes like something like this. So it's kind of 7.5 divided by the optical depth just within a blockade radius to the 3/2 power. So theoretically, it's possible to generate a gate in a disordered ensemble. But then you can ask, is it possible to achieve a better scaling using an atomic array? Any questions so far? Uh-huh.
You said that you can excite atoms to the Rydberg state just when they are in the distance larger than the Rydberg radius.
Right.
But in this picture, you draw surface that in that just the atom with a distance lower than the Rydberg state are excited.
Oh, you mean this kind of cartoon here?
Yeah.
Oh, okay, yeah. So sorry, like without Rydberg blockade, I tried to explain that like if you reflected a photon, one atom had to be excited, right? So from the standpoint of a second photon, you've punched a hole in the mirror. So that's this kind of red dot here. So now, like with Rydberg blockade, it's kind of similar. So let's imagine that this one atom in the middle was responsible for reflecting a photon. So that one is certainly punched out, so it's colored red. But now, because it was in the excited state, it turns on this Rydberg blockade effect. So it shifts the excited state levels of all the other atoms nearby, basically to infinity. So effectively, now you can't, I mean, those atoms have now effectively disappeared from the system as well.
So in this area, if you send the beam,
It's effective, I mean, yeah, so the physical atoms are still there, but they're impossible to excite optically anymore. So effectively, that's what I mean by the red. It's like you just kind of punched a hole in the array where they don't matter anymore. Yeah, so the red indicates this kind of punched hole.
Yeah, you were talking about simultaneous reflected photon, but is there what's the typical time scale of this?
Okay, yeah. So so one thing you can measure is G2 as a function of delay time.
Yeah.
So so here I'm looking at simultaneous photons, but if you were to look at G2 of t, it basically recovers to 1. So the characteristic kind of time scale here is the spontaneous emission time of atoms. So more precisely, it's not the individual atom's spontaneous emission rate. It's actually the collective emission rate of the kind of collective mode that participates in this reflection. But for practical purposes, they're not so much different from one another. Oh yeah, and I guess a kind of related point is, so that's why it's not exactly a kind of, I mean, so you can think of this effect as so far as a saturable mirror, but it's hard to turn into a gate simply because there are these issues of timing, right? Like, this effect kind of disappears after this time scale of the spontaneous emission time, and that's what makes it difficult to turn it, without playing these extra tricks that I'll describe now. It's hard to turn that into a high fidelity photon-photon gate. Okay, so now I'll kind of illustrate just briefly explain the general protocol for realizing a high fidelity gate. I'm not going to explain so much the details of the calculations or the physics, simply because I think it kind of just recycles a lot of the ideas we've already discussed previously. So the kind of strategy to realizing gate is to basically use photon storage, which kind of gets rid of this kind of transient effect of the saturable mirror. So basically the idea is that we have photons A and B, and we can specify that photon A is going to come first. Okay? So photon A arrives, and what we can do is we can try to use photon storage, or quantum memory, to store this photon, to convert this photon into one Rydberg excited state. And then the result is the following. So again, so this mode A is kind of like a qubit. It can have 0 or 1 photon. If there's no photons, then this storage doesn't really do anything. I still have my kind of original mirror as before. But now if I kind of store this one atom, this one photon into a Rydberg state, this photon blockade effect turns on, and it effectively punches a huge hole in my mirror, but for a kind of arbitrary time, right, until I retrieve this one photon again. So basically, again, I won't go into details, but you kind of naively expect that this gate should be highly efficient because, first of all, the quantum memory performance should be enhanced by the array. In 1D, we show that you get an exponentially improved, exponentially suppressed error rate for a quantum memory. And at the same time, we expect that once we kind of create this kind of conditional state, photon B will be either perfectly reflecting or perfectly transmitting without kind of scattering into random directions. That suppression of scattering into random directions is due to the spatial periodicity of the system. Provided that, just as long as the blockade radius, this kind of punched hole size, is bigger than the beam waist. Okay? So the beam waist starts to become comparable to this blockade radius. You'll start to notice this kind of aperture, the atoms on the edges, and that will cause the second photon to start scattering into random directions. So you can just kind of do the numerical calculation. So what I'm plotting here is the gate error as a function of the blockade radius. And there's one optimization parameter we can play with, which is the kind of beam waist of these modes A and B. So it's already optimized over this beam waist So the blue dots are just kind of full numerical calculations with the spin model. So here's on a log scale, the error of the gate as a function of blockade radius. So you see that kind of goes down pretty quickly. It's a little bit involved, but in principle, you can kind of construct a simplified toy model of how you think this gate works. That produces some analytical estimate of what the error is as a function of blockade radius. And you see that this kind of theoretical curve fits pretty well with the numeric. So we think we know, pretty well what's going on. And I guess, maybe the kind of thing to point out is that, the error scales like increasing blockade radius, like 1 over r to the 4th power. You can go back and compare that to the Maxwell-Bloch equations for a disordered ensemble. There, the gate error, the best known gate, is known to scale like 1 over the blockade depth, blockaded optical depth to the 3/2 power. So the blockade optical depth obviously depends on the blockade radius as well, but it also depends on other factors. In particular, it depends on the density of atoms. So it's not completely straightforward obviously this 1 over 4 looks better than 1 over 3/2, but because here there's a density involved, it's not completely straightforward to compare. So maybe the best comparison you can do then is just, from a practical perspective. Let's look at state-of-the-art Rydberg experiments in disordered ensembles. So in those experiments, you can achieve a blockade radius these days of something approaching 20 microns, I believe. And once your blockade radius approaches 20 microns, just for the disordered ensembles, the cold atomic ensembles that are used, you get a blockaded optical depth of something around 5 to 10. So if you plug that into this formula here, you get a gate error of something like 25%. On the other hand, if you take this kind of blockade radius and apply it to this kind of atomic array, you would find a gate error of something like 10 to the minus 3. So again, it illustrates that interference is a potentially powerful effect. I'm not exactly sure about the timing. So let me maybe skip this section for now and return to it at the end if I have time. Basically, the main message is, so far everything I analyzed, if, for example, the quantum memory or now this kind of photon-photon gate, is still with a relatively few number of photons and excited atoms, 1 or 2. So that makes the spin model still tractable from a numerical perspective. But recall that, the full spin model, if I'm allowed to excite many atoms, it has a Hilbert space of 2 to the n. So that sounds kind of like a hard problem, and it is. But I guess the goal of this kind of short discussion was to show you that there are limits where you can actually deal with this many-body complexity and see interesting stuff coming out. So that's the message. If I have time, I'll kind of try to explain it more at the end. Okay, so now I'd like to kind of switch gears. Thus far, I tried to focus on the potential consequences of wave interference in quantum applications involving atoms and light. At the beginning, though, I mentioned as well that if you have some kind of alternative theory that really includes interference, it might just be interesting from a fundamental standpoint as well. For example, it might allow you to identify new phenomena or get new insights into existing fundamental phenomena that one did not have before. So now I'd like to give an example of this type of fundamental physics. So I'm going to start with just kind of a crazy, simple observation. Just not in terms of, so it has nothing to do with quantum optics or atomic physics or quantum devices. But let's just talk about optics. Okay. So we have many different kind of optical devices made out of many different materials. You can have oil, water, glass, silicon, diamonds, you name it, right? But out of all these kind of optical materials that we have at telecom and visible wavelengths, if you think about it, all the materials you know of have a refractive index of order 1. Right? So silicon is considered high index, but has an index of around 3.5. So that's kind of weird, right? I mean, there's not a single material with an index of 10, at least in kind of in the optical domain. And so that might kind of lead you to ask the following questions. Is there kind of universal physics governing this refractive index and how large it can be? And kind of likewise, if you kind of understand why the index is of order 1, if you can maybe find some way to get around that, that would have profound technological implications in optics and photonics. Just to give kind of one example, the index is of course important because it dictates how much you can shrink the wavelength of light in a material relative to vacuum. Okay? So, you know, and thereby dictate the size of the optical devices that you can create. Imagine, for example, that you can make an index of 100. Then you can start building waveguides that are about 10 nanometers in diameter. Okay? And 10 nanometers is kind of neat, just to give one example, because that's a similar size as the size of individual transistors, electronic transistors. So if you can make waveguides the same size, you can now imagine putting waveguides into your computer processors and using these waveguides to route information around. So this is just, you know, completely hypothetical and speculation, but I think it kind of illustrates the you know, potential of having ultra-high index materials. So that's a kind of provocative question, right? Why is index of order 1? And it's kind of one of these strange questions where, to my knowledge, no one really has the answer, but a lot of people think they have answers, or at least kind of, you know, hypotheses. So let me at least try to kind of rule out a couple of the most prominent kind of conjectures. So one is that, you know, when we work with optical materials like glass, we typically work far away from their natural electronic resonances. Just to give one specific example of that, let's just take the index of silicon as a function of wavelength. So the band gap of silicon lies somewhere out here, somewhere around 1500 nanometers. So we use silicon in that regime because then silicon is highly transparent. It has an index of around 3.5. Somewhere around here, the wavelength of light is short enough that now you can start to excite interband transitions within silicon. So then the kind of extinction coefficient of silicon in green starts to shoot up naturally. And you see that the real part of the index starts to increase as well, but it's not by an order of magnitude. It jumps maybe up to close to 7. Okay? So again, I think it's fair to say that the refractive index is still of order 1. You might also just say that, well, real materials are complicated. You know, how can we talk about, you know, index, and there must be all kinds of effects that make the index small? Maybe one candidate is, for example, phonons. But that's not really a kind of satisfactory answer either, I believe, because, you know, if phonons are involved, you expect a very strong dependence on temperature. Right? As you increase the temperature, the material starts shaking more and more, and your phonon occupation number explodes. But then when you look at the optical properties, again taking silicon, you find that over the entire temperature range where silicon is a solid, the index only changes by about 10%. Okay? So it doesn't really seem like phonons are really a part of the fundamental answer either. So those are just kind of suggestions. You know, I'm not trying to make rigorous arguments at this point. But, you know, if we believe that the origin of index and its limitations is more fundamental, maybe we can just create a very, very minimal model. So what if we create some kind of, you know, toy material where we can look at, you know, the optical response near resonance, and just to kind of simplify things, what if we just make this material free of any kind of chemistry and solid state interactions? So there's a good approximation of such a material, which is just an ensemble of well-separated and stationary atoms. When I say atom, again, I'm just going to take this kind of minimal model. It's a two-level system with one optical transition of interest. It has some resonant wavelength lambda Eg, and a single isolated atom has a radiative line width of gamma naught. And one thing kind of interesting about this kind of, you know, hypothetical material that we created is that the individual elements of this material, these single atoms, have an optical response that's completely well understood, right? So there's no kind of ambiguity or confusion about the individual elements. In particular, you might recall from the first day that I said that, you know, one kind of interesting characteristic of a single atom is that, you know, if you have a single atom and you take resonant light and you focus it onto the atom with some area A, you can ascribe to the atom some scattering cross-section. And that resonant scattering cross-section actually doesn't depend on any details, microscopic details of the atom, but it's just given by the resonant wavelength squared. And why that's interesting, especially in this kind of, in the context of this discussion here, is that a typical optical transition in an atom can have a wavelength of around 1 micron, but the physical size of an atom, as characterized by the Bohr radius, and also, the kind of characteristic interatomic spacing in a real solid, is something like a tenth of a nanometer. Okay, so this single atom has an extraordinary optical response compared to its physical size. And now, once you kind of realize that, you can easily get confused. So for example, let's create a hypothetical material where it's just a kind of cubic wavelength box, and let's just put one atom inside. So by the previous argument, I know that this presence of one atom in this cubic wavelength box is like the atom effectively occupies the entire box from the standpoint of scattering light. So it's like a kind of dielectric material where the refractive index is already noticeably different than 1. So if one atom already has that effect, what if I put in 10 atoms or 100 atoms? Shouldn't the optical response kind of grow and grow? And then shouldn't I be able to realize some ultra-high refractive index? So of course, the refractive index of an atomic ensemble is a kind of textbook problem. So for example, you can use the Maxwell-Bloch equations, or more broadly in optics, there's something called the Rydberg-Lorentz equations, which are equivalent for these purposes, which tell you what the refractive index should be. So in particular, they say that the electric permittivity, which is just the index squared, is proportional to the polarizability of a single atom times the number or the density of atoms that I have in my ensemble. But now there's the following problem. So if you take a realistic atomic polarizability and you just put in some frequency that's close to resonance to kind of guarantee a huge optical response, if you plot out the index, how big can the index be as a function of atomic density, you get the textbook gives you a curve like this. Okay? So by the time you reach the density of a real solid, these formulas would predict an index of something like 10,000 or 100,000. Whereas we know that kind of empirically that real materials kind of sit here. They have an index of order 1. Just to provide some additional context, typical cold atom experiments sit somewhere in this regime here. And if we're going to be kind of a little bit more intellectually honest, we should acknowledge that, well, when atoms become close enough together, like a few nanometers, quantum chemistry starts to turn on. So maybe I shouldn't take these formulas so literally anymore. But nonetheless, you see that there's no obvious way to connect this black curve here to this point here. And so that's what I like to address in the following. So of course, we already know that the Maxwell-Bloch equations are really just a kind of convenient macroscopic theory for atoms and light. But they do have the issue that they throw out multiple scattering and wave interference, which kind of we know can be important for dense media. So even this problem, is kind of well known historically. I'm not the first one by far to point this out. So there have been various attempts to try and incorporate, at least at some approximate level, the effects of multiple scattering into the formulas for refractive index. And maybe the most famous models historically are known as the Lorentz-Lorenz, or equivalently the Clausius-Masati equations. So the kind of intuitive idea of these equations or these models is the following. Imagine I have one atom J, which I kind of just pick out as being special. And in principle, I know that this atom J sees the rescattered field from all the other atoms nearby. So what these kind of models say is that it's very hard to talk about to include all the kind of granular effects and so on. So let's just approximate all the other atoms as some smooth dielectric background with some refractive index n, except for this kind of little spherical exclusion of vacuum whereby one special atom sits. So the nice thing about this kind of dielectric geometry is that when you have a polarizable material with some sphere inside, it's easy to calculate what the induced field is inside the sphere coming from all the polarization density around it. So that gives you some estimate of what the rescattered field from all the other atoms is. And then you can basically self-consistently solve for the refractive index. So when you do that, though, and you do this specifically for near-resonant atoms, that answer still seems insufficient. In particular, the spectrum of the refractive index, as derived from this Lorentz-Lorenz model, is actually identical to that of the Maxwell-Bloch equations except with some kind of frequency, or with some density-dependent shift in the overall spectrum. So in particular, the Lorentz-Lorenz model still predicts an index of 10,000 for a real solid. Okay, so now let me kind of go back to this kind of more microscopic models, coupled dipoles. So just to make it a little bit more specific, we'll only be interested in the linear refractive index, so no nonlinear effects. So within a kind of spin model, that means we can just shine in an arbitrarily weak input field and look in this kind of single excitation regime. As I explained before, this regime here is also completely equivalent to the physics of classical coupled dipoles. So you can use either language here. Just kind of to choose one concretely, I'll go back to this kind of language of classical coupled dipoles. So sigma, so ground and excited states of the atoms have kind of disappeared, and I instead talk about the atoms as just kind of polarizable point dipoles. So again, the kind of question we want to solve is, we have a collection of dipoles, or atoms J, where J goes from 1 to n. And in particular, when I shine in a field, I can formally write down an equation for what the induced dipole moment is. That's just the polarizability times the total field. And again, the challenge is that the total field is not just your incident field, but includes the fields coming from all the other dipoles in your system. So again, this is just a kind of big linear set of equations. You can write it in terms of big vectors and matrices and solve it by matrix inversion. And again, I want to emphasize that this is formally exact, so it includes multiple scattering and wave interference to all orders. And then again, once you have these once you know what the dipole moments are, you can calculate any property of the total field just by this kind of input-output relation. So I should say that there's already been a significant body of work on the optical properties of dense gases, both theory and experiment, including from Antoine and Jean-Jacques, among others. And I think it's generally known in this community that one must go beyond the Maxwell-Bloch equations. This includes multiple theoretical and experimental observations that the optical response of a dense atomic medium is smaller than the Maxwell-Bloch equations predict. But I think it's fair to say at the same time that the underlying physics is still elusive. And what I mean by that is, although in principle in this kind of linear regime, all the physics is contained in this kind of coupled dipole equations, it's really a microscopic theory, which means that the number of equations that you have, the number of eigenvalues and eigenstates, grows explicitly like the number of atoms. So it's just kind of too much information. Sure.
This question is, when we use a green functions approach to this kind of explanation, is it necessary to consider all the atoms? I think the green function relates one particular atom to all other positions around that atom. So is it necessary to do it for the entire array of atoms to consider?
So that would give strictly the correct answer. So I guess what you're asking is, so this equation here formally connects one atom to every other atom. So it's a full rank matrix.
If it's not necessary, then it would reduce the dimension.
Right. So that's a very good point. So one could, of course, look for approximate theories, either kind of macroscopic or semi-macroscopic, semi-microscopic. Then it's just a question. So I don't know of a particular approximation offhand that you can kind of justify a priori along the lines that you described, but I can't rule it out either. Yeah, so I think there's actually a lot of room for just development of new ideas and approximation and approaches in general. Yeah, so basically, the coupled dipole approach is in principle exact, but it's too much information. If we believed that this kind of microscopic approach was generally a good approach to doing physics, when you open up an optics textbook, it would start by explaining a prism works by looking at its 10 to the 23rd eigenstates. Okay? So it's just not a viable approach in general. So now I'd just like to briefly introduce some of the numerics that we do to extrapolate the index of a dense medium. So the numerics is, in itself is nothing deep. It's just the kind of equations that I presented earlier. But there's kind of a few specific tricks we play, which I think make it slightly easier to pull out the index in an efficient way. So I want to go through some of those subtleties. So if we don't talk about numerics, but just about kind of concepts, I think we all know one easy way to extrapolate the index of a material. So imagine kind of experimentally, I can take the limit of of an infinite slab, so infinite in the transverse direction. I can come in with light that's more and more extended, so I approach something like a plane wave. And then I can easily write down in concept that the outgoing field is some transmission coefficient times the input field. This transmission coefficient can be complex, but I can rewrite it in this form, e to the I omega over c times the index times the length of this slab. So once I know the length, I can easily go, at least in principle, and extract the index. When we do numerics, and here I'll focus on disordered systems, obviously we can't create an infinite number of atoms, so we try to approximate this as best as we can. Our infinite slab is going to be an extended cylinder where we can have atoms occupying inside with random positions. And then, in practice, we can get up to about 30,000 atoms randomly distributed. And anytime we calculate observables, we're going to average over many microscopic configurations. And then for our input field, we're going to come in with a focused Gaussian input. So it's not going to be super tightly focused, but the beam waves is just going to be small enough that the beam doesn't really see the edges of the cylinder. That avoids kind of complicated diffraction effects from the edges, which make the interpretation of what comes out more complicated. So now we solved the coupled dipole equations. We obtained all the dipole amplitudes. And in principle, we can calculate the field with this input-output equation. But it turns out that's not so convenient in practice. Because this input-output equation is really at discrete points in space. So if I want to calculate the field at different points, I have to repeat the calculation many, many times. That's very time-consuming. And furthermore, we know that this kind of outgoing field, if I look in every direction, contains this kind of complex speckle pattern, right, from the wave interference. So to fix that, what you can do is there's a formal mathematical procedure where you can take this field in space and project it into the same Gaussian mode in the transmitted direction. When you do that, you just reduce everything to a single number, the transmission coefficient, back into the same mode that you sent in. And that allows you to calculate the transmission in one shot. And again, you can write this as e to the I, k, and l. Once you know the length of the cylinder, you can extrapolate the index of the medium. Questions on this part? Okay. So let me just kind of show some typical numerical results. So there's a lot of information on this slide, so I'll try to explain it a little bit slowly. So on the vertical axis here, I'm plotting the real part of the refractive index. And then on the horizontal axis, I'm plotting the frequency of the response, or the frequency of the light that I'm sending in, relative to the bare atomic resonance frequency. Okay. So these different solid curves here are the numerics, and they show different increasing densities. So green is kind of just a few atoms per cubic wavelength. The highest densities we can go out to are maybe something like close to 1,000 atoms per cubic wavelength. And then the dotted lines show the Maxwell-Bloch equations. So these Maxwell-Bloch equations, maybe not so surprisingly, show that when you go to very high densities, the index just seems to explode. So you clearly see kind of a deviation from the Maxwell-Bloch equations once you have around 100 atoms per cubic wavelength. I mentioned at the beginning that it would be nice to try and look for some kind of universal physics in the index. So you can already get a hint of that here. So if you just take the curves at the few highest densities, like the orange and red curves here, you can just replot these curves. But instead of the horizontal axis simply being the frequency, you can rescale the frequency by the atomic density. And what's interesting is when you do that, all these curves basically kind of collapse onto the same function. So the key point is that you get an invariant, rescaled spectrum at high densities. And in particular, if it's a kind of universal function, you see that no matter how high a density you go to, the maximum index that you achieve is always going to be the same value, 1.7. And so that's nice. It's a very minimal model, and maybe we're a little bit lucky, but nonetheless, we do recover a real-life value of refractive index. So that's just kind of pure sorry. Oh, so for lower density, it's not universal, and that's simply because if I take the limit of no atoms, then I'll trivially have an index of 1. So for low densities, you do get this kind of increase of index with density. But then once you reach kind of a few hundred atoms per cubic wavelength, you tend to kind of collapse onto this universal physics. Exactly. Right. So this is just numerics. We can't push the numerics much further. But now I'll introduce an effective theory, which argues that that should be true. And in particular, which also avoids this complexity of the full couple dipole model. So to introduce this kind of theory, let me just start with a simple example, that of only two atoms. So if I have two atoms or two dipoles very close to each other, I know that they should interact very strongly through this kind of 1 over r cubed near field. So what that means is that I shouldn't really consider these atoms or these dipoles as independent modes anymore, but rather the eigenmodes of the system will consist of symmetric and antisymmetric modes. So one mode is that you have two radiating dipoles which are oscillating in phase, and then the other mode is that the two dipoles oscillate out of phase. So these collective modes will have different properties than individual atoms. In particular, it's maybe intuitive to see that because these two dipoles are oscillating in phase, they radiate energy faster than that of an individual atom. It's basically like a giant dipole. So the emission rate of this collective mode is actually twice that of a single atom. And likewise, these two dipoles tend to kind of cancel each other out. So the collective emission rate actually goes to 0 as the distance between the dipoles goes to 0. In atomic physics language or quantum optics, this is also just the kind of two-atom limit of Dicke sub and superradiance, if you're familiar with that. Maybe more important to the discussion, though, is in addition to this kind of renormalization of decay rates, there's also a strong renormalization or shift of the resonance frequencies of these collective modes. So basically, one atom gets strongly dressed by the field coming from the other atom, and that leads to an energy shift that goes like 1 over the distance cubes. So far I talked about just the kind of eigenmodes of two dipoles, but now let's consider the consequences when these two particles interact with light. So that's, imagine I put it in some kind of input field, and for example, I can look at I can, for example, plot the scattering cross-section of this collective system as a function of frequency. So just to normalize the discussion, recall that for a single atom, well, you expect a kind of Lorentzian line shape. And then the maximum scattering cross-section on resonance is just going to be lambda squared. And so the point is, because of these kind of strong dipole interactions, the answer for two atoms is not just going to be twice that of a single atom, but instead you're going to see two distinct peaks. They have distinct centers corresponding to the shifted resonance frequencies and different line widths as well. So now comes the key point. So I argued that this kind of curve, this spectrum here, is a result of two identical atoms which are strongly interacting via the near fields. But at the same time, because these are just kind of, to very good approximation, just kind of isolated Lorentzians, there's another system that can cook up that gives you exactly the same answer. I could have just given you two different atoms with different resonance frequencies in the first place, where I shut off the near field interactions, and they would produce the same answer. There's fundamentally no way, at least in terms of the optics, to tell these two cases apart. So I've mapped a problem of two strongly interacting atoms, or two strongly interacting dipoles, onto an equivalent system of non-interacting dipoles, or resonators. So now we can apply that same argument to a many-atom system. So the idea is that when you have spatial disorder, statistically, you'll have some pairs of atoms that are extremely close to each other. And that implies that they'll interact with each other much more strongly through these kind of optical near fields than with all the other atoms combined. So what I can do then is I can take this kind of Green's function matrix that describes the interactions between all atoms. I can do something like perturbation theory. I can say that the dominant term is a kind of 2x2 matrix just involving the near field interaction of these pairs, plus everything else as a perturbation. And then I can diagonalize this 2x2 problem first. That's exactly what I did on the previous slide. So basically what I can do is I can replace these two strongly interacting identical atoms with two new atoms of different resonance frequencies and with the near field interactions turned off. But then I can repeat this process over and over. I can find the next most strongly interacting pairs, renormalize them, and so on. Okay, so this process is known as strong disorder renormalization group. So by the end of the process, I've basically eliminated all the strong near-field interactions from the system and only left far-field interactions with light behind. And also the product of that is that initially I started with a homogeneous atomic medium. So basically, if I were to plot a probability distribution of resonance frequencies of the atoms, the physical system is just a delta function. But what I'm saying is it's optically equivalent to an inhomogeneously broadened system with a non-trivial distribution of resonance frequencies and with the near-field interactions turned off. So here's the kind of numerics for the RG. These are just, again, different densities. You see that as you make the density larger and larger, the amount of inhomogeneous broadening gets bigger and bigger. Again, you can look for universal physics. So you can take all these curves here. And again, you can rescale the frequency by density. And then you see that all these curves collapse onto the same function. Okay, so this really shows kind of universal behavior. In more condensed matter language, this is called the fixed point of the RG flow. And so now you see just directly the amount of inhomogeneous broadening scales directly with the density of the medium. So now you can finally understand why the refractive index of this atomic medium saturates. So imagine I have this kind of atomic medium. I know that I can replace it with this renormalized ensemble. And imagine I shine in light of some frequency. So the point is, no matter what frequency I choose to send light in, even though my physical density of atoms per cubic wavelength can be very big, because all the atoms start to acquire different effective resonance frequencies, actually the number of near-resonant atoms with this frequency here is always going to be limited to about 1 atom per cubic wavelength. So no matter what, the light that comes in only sees about 1 atom per cubic wavelength to efficiently interact with. And that's what limits the density. So you can go on further. You can compare with full numerics. So here's the couple dipole simulations I showed earlier. Here's the textbook prediction where the index explodes with density. And just to check that this RG is really kind of correct, you can take this hypothetical system. You can again run these kind of couple dipole simulations, and you see very good agreement with the full answer. So now I think we're finally in a position to understand why conventional theories of refractive index fail when we go to these kind of resonant atomic media. So when I say conventional theory, I mean kind of macroscopic or practical. And when I say practical, almost inevitably, you have to ignore the granularity, right? You don't want to keep track of all the atomic positions. So you need to make some kind of smooth medium approximation. The Lorentz-Lorenz example is a good example of that. You take all the other atoms around one particular atom, and you just smooth it into a kind of some kind of dielectric background. But now if you believe in this kind of renormalization group, you see why that argument is incorrect. Because the renormalization group argument says, no, the other atoms are not a smooth background, but it's really the one nearest atom that matters the most and which dominates the optical physics. Fortunately, the RG also provides a method to develop a more accurate, smooth model theory. So in particular, the RG says that the atomic medium is optically equivalent to an inhomogeneously broadened ensemble. And then if you take this inhomogeneously broadened ensemble and plug it into a modified version of the Maxwell-Bloch equations, then you can finally get the right answer, or a good approximation for the maximum index. So again, I asked this kind of provocative question, why is the index so small? Admittedly, what I've told you now is just a kind of small part of the full story, but let me try to kind of extrapolate a little bit further. So again, here's the kind of issue I showed before. The textbook theory predicts a huge index for solids. That's not what we see. What we showed so far is that in the kind of dilute regime before chemistry turns on, if you have a disordered medium, the refractive index maximizes to about 1.7. I don't know exactly what happens when chemistry turns on, but there's kind of one obvious hypothesis that you can make, which is that this thing just continues in a straight line. So the chemistry might, of course, affect the microscopic details, but the essence of RG is still correct. It would be interesting so that's just a kind of guess, but it would be interesting to make that more scientifically concrete. And that's an interesting problem in itself, because ultimately you have to combine the theory of multiple scattering of light with quantum chemistry, which really hasn't been done in a non-perturbative regime before. Of course, disordered materials are only a small fraction of what we have in real life. We can also have crystals. It turns out that, so actually if you repeat the same calculations, you can kind of convince yourself that the index of a crystal within this kind of point dipole model actually does increase indefinitely with density, albeit at a slower rate than what the textbook says. So that's true, though. That also makes this kind of problem of combined multiple scattering in quantum chemistry more interesting, because it suggests it's really some aspect of quantum chemistry that shuts off this huge index and brings you back to order 1 in the end. So I guess over these past 3 days, I tried to give you a few examples of how including interference in quantum light-matter interactions leads to interesting consequences, both application-wise and fundamental. Normally in a school, I'd conclude by kind of giving a broader overview of where this field is and where it might go. I don't know how to do that here because I think the field is just so new and there's so many unanswered questions and directions that just even haven't been defined yet. So I don't know how to do that, but maybe my kind of final concluding sentence is that hopefully now you guys all believe that this topic of quantum light matter interactions, including interference, is really kind of an unexpected and an exciting frontier.
Thank you very much. Questions? Yes?
Yeah, so I mean, I only kind of briefly alluded to it here. So if you do the numerics, you get what's actually kind of a density to the 1/3 scaling. You can develop an analytical theory for it as well. What we're trying to do now is actually get into this quantum chemistry regime. So when you include chemistry, can we really show that the index goes back to order 1 by the time you reach a solid? So that's right. So it's actually kind of interesting. I mean, so basically, it seems like when you have real materials, whether they're disordered or crystalline, it's kind of maybe more of a coincidence that they both have an index of refraction of order 1 in the end. So it's not universal physics for the 2 different cases.
Do you know about methods to experiment in the museum on just before chemistry?
Here.
Yeah.
Yeah, so it's not possible. Well, I think at the moment, probably no one knows how to make cold atoms with that kind of density. But the interesting thing is you can also consider solid state systems. Like you can consider, for example, silicon vacancy centers, which are kind of effectively like artificial atoms in diamond, or maybe rare earth ions doped in a solid. So there you can reach significant densities. And that might be a kind of interesting platform to explore these effects.
Are there any metamaterials or photonic crystals that claim also to increase the refractive index? And ultimately, can you do some kind of this arrange material with the new arrays of atoms?
Okay, yeah, so that's a really good question. So here I really focused on the properties of bulk materials. So of course there's this huge field in photonics where once you have some bulk index that's not 1, you can start to shape things, create photonic crystals and so on. You can create very slow group velocities. So you can get a lot of, and create strong phase shifts for light. So you can get a lot of control that way. And so, right, so that's a whole rich topic on its own. But I think it's fair to say that, photonics only exists because you have refractive index in the first place, right? And so if you could have an index of 100, I think that would give rise to new types of photonic devices that you couldn't generate with just index of order 1. So that's more the kind of motivation of this discussion. Right. Yep. Uh-huh. Yep. Yeah, so that's a great question as well. We haven't explicitly done the calculations, but I think it's kind of well known that here we're only considering disorder. So when you have disorder in scalar waves, when you go to a high enough density, you get an Anderson localization transition. So then things become just kind of so random and crazy that it probably doesn't make sense to talk about. It doesn't really have an index anymore, right? So it's a little bit, I mean, it's a little bit vague because I simply don't know. I mean, that's the short answer. So quantum chemistry, of course, there's two ways to view it. Like, there's the whole field of quantum chemistry, which is about developing, good approximations to treat this insanely complicated problem, right? But, we can maybe take the kind of, and so quantum chemistry contains a lot of different effects in principle. It contains that, atoms have orbitals which can hybridize. There's electron-electron interactions. There's fermionic statistics, and so on. So full quantum chemistry would include all of that. If you do exact quantum chemistry, though, we know that you would just reproduce exactly what you see in everyday life, which is the index of order 1. So I think what you really need is something more subtle. You don't want to just do exact quantum chemistry, but you have to identify among all the effects that chemistry includes, which is the one that really matters for the index. So if you were to turn on and off different effects, like turn off fermionic statistics, does that really matter at a kind of qualitative level, or is that really just some kind of detail? So I think that's really the challenge going forward.
And you have proof of about which of these effects is different for crystals and
Yeah, so I can tell you my guess. My feeling is it's not actually any super complicated quantum aspect of quantum chemistry. It's really just the finite size of atomic orbitals. So far in this kind of point dipole limit, I really think I say my atom is a delta function in space. But in real life, the thing that scatters the light is really the electron, which is kind of smeared out by amount of the Bohr radius. And I think that kind of smearing becomes important once you get a reduction in wave. So here you get a bigger and bigger wavelength. But once that reduced wavelength becomes comparable to the smear of the wave function, my guess is that from the standpoint of optics, it starts to look more like a disordered system. And maybe this kind of physics of renormalization group starts to take over again. So that's just kind of pure speculation, but yeah.
Maybe just a small, so using just a small maybe comment to say that using in microwave engineering, so with superconducting circuits, in fact you have some using in TEM mode, using Josephson inductance or net inductance with very disordered superconductors. It is actually possible to get very slow and broadband, I mean, exactly.
Right. Yeah, so actually, yeah. Well, so I think there's kind of like effective index, like how much is group velocity slowed. So in optics, again, once you create, photonic crystals, you can achieve that as well. So here I'm talking more about like the bulk. But
Is a bulk also in a sense. It's not related to some nanostructure.
Okay.
It's a broadband, and it's not like a resonance phenomenon.
Okay, sure.
Between the simulation of near-field interactions and initial simulations of refractive experiments, there was a drastic difference between the number of atoms displayed in the field. So is there a reason why one of them is positive?
Oh, yeah. So yeah, that's a great question. So when we do the couple dipole simulations, we do really have to invert this, n by n matrix. So that limits the density there. In this renormalization group theory, it's just really a kind of 2 by 2 game. So you never have to go and explicitly invert this giant matrix. You just go, you can take a huge number of atoms. You just go look for the closest pairs. You replace them with new atoms and new atoms. And then by the end, you can get this kind of effective probability distribution of resonance frequencies. So that's what allows us to go to just, much larger densities in that case.
We're going to stop here. Thank you very much, Derek. You are still around until tomorrow evening.
Yep, right.
So if you have questions, please go see Derek. So there will be you left.
So you had 2 excellent questions.
All right. So we